Okay, so we are talking about cosets. So, we have discussed the left coset. Today, we will define the right coset, and then we will talk about the normal subgroup. Okay. So, let us have a group G. G is a group. Let G be a group, and H is a subgroup of G. So, these are all non-empty. Okay. So, H is a subgroup of G. So, we have a group G and we have a subgroup H, which is a subset and which is happen to be a group again with the same operator star. Now, we define the right coset. So, let A be an element from G, any element, we define this for any element. So, H A. So, H A is basically set of all element H A, where H is coming from capital H. Okay. So, this is the operation is basically star, but sometimes we can just write H A, but this is H A means H operate with A under this operation. Okay. So, this is the right coset. Left coset we define A H, which the operator is this way. So, this is the other way around. So, this is we call the right coset. So, for example, if we have say if we have a group like say Z n. So, say G is equal to Z n plus and say H is equal to 3 Z set of all integer which is multiple of 3. Okay, then we can define H plus. So, this is a additive sense operation. H plus 0 is basically H, 0 is the identity element, H plus 1 is basically set of all integer of this form this. So, H plus 2 is basically 3 n plus 2. Now, again H plus 3. So, these are basically H plus 3, this is basically H 3. I mean this we can use star, but star here is plus. So, that is why it is this symbol. So, anyway these are the notation basically. So, H plus 3 is basically H 3. So, this is nothing but again this will be H, because this is 3 n plus 3. So, this is again H. Not only that, if you take any other element, so if you take H plus 6, 6 is also belongs to H, H plus 6, that will be also H. Okay. So, this is general result. So, what is the result? If you take any element from H, so we have this group, we have this subgroup. If you take an element from H, then H is basically H. Okay. This is true for this we can prove. Similar proof we did for left coset. So, similar argument will be here. So, this is a result that if you take any element from H and if you do this, then it will give us H again. Now, this is theorem 1 we can say. Now, theorem 2 is if you take an element which is not in H, which is here. Okay. So, A is basically belongs to G minus H, which is not in H. Then H A and H are empty. So, H A basically this, they have no common point. Okay. This also we similar proof we did for the left coset. So, similar argument we can carry over here. Okay. So, now this is another result. Now, another result is, now if you take any two element from A from G. So, this is our G. Now, if you take any two element A B, now this is say H of A, this is say H of B. Now, this theorem is telling, sorry, this is H of B, this is the, these are two left coset, sorry, right coset. So, this theorem is telling either they are same or they are disjoint. So, this is the theorem, any two right coset are either same, that means H A equal to H B, or they are disjoint, or they are disjoint. So, that means the disjoint means H A intersection H B is empty. Okay. So, either they are same or they are disjoint. So, when they will be same, so this is so this proof are already there for the left coset. So, similar proof can be carried forward here. Okay, this is one theorem. Another theorem is now if B belongs to H of A, then B belongs to H of A if and only if B inverse belongs to H. This is also necessary and sufficient condition. So, if this B belongs to this, then this part is okay, and so in that case H of A will be H of B. Okay. So, this relation, so we defined a relation between, so we have a set G, now we take two element, now we defined a relation A related with B if and only if B A inverse belongs to H. Okay. So, now this is an equivalence relation, like we did similar thing for the left coset, this is for the right coset, similar argument we will carry forward here. So, this is an equivalence relation, we can prove that this is reflexive, symmetric, transitive. So, this relation is an equivalent relation. So, and if it is an equivalent relation, it will give a partition on the set, and that partition is nothing but our this coset, distinct cosets, disjoint, and we know the cosets are either disjoint or they are same. So, that is basically our class of the this thing, class of the equivalence classes of this. So, we define the equivalence classes. So, we define equivalence classes so CLB is basically nothing but H of B, that means it is set of all element such that they are related with this, that means it is basically X such that B X inverse or X B inverse must belongs to H. Now, this is nothing but set of all G X such that X belongs to H B. Now, this is nothing but the set H B. So, if you take a element, so that will form a class, equivalence class, and this will give us a disjoint class. So, this will, so if we have this G, then if you take a element B, so it will form a H B, another set A, so H A. So, these are all disjoint set H C, either they are same or they are disjoint. When they are same, if they are related, if this condition is satisfied, if they are related, then they are same, and basically they will be give the same subset then. Okay. So, this will form a partition, and this partition will be disjoint collection of the subsets. So, this will form just partition on this, so just a disjoint partition like this. So, H of A, H of B, H of C, H of D like this, H of E, H of E is the identity, that is basically H like this. So, G is nothing but union of this partition. Okay. Again we can prove that what we did in the for the left coset, the number of element in each right coset is same. So, this is another theorem. This theorem is telling the number of element that means cardinality of two right coset this class are same, number of element in every right cosets are same. Okay. This proof we this similar proof we did for the left coset. We have to take a function, bijective function from one coset to another coset, then we can say this is the same cardinality, and that is H is one of this coset, H is one of the coset. So, that means H is dividing this, H is forming this partition with equal number of element as H is having. So, each coset has having the equal number of element with H. So, these sets are subsets are having same number of element with H. Okay. So, this is basically this proof we did for the left coset path, and this again we can prove the Lagrange's theorem if G is finite. So, if G is finite, then cardinality of G is basically summation of cardinality of H and number of cosets. Number of cosets, if it is finite, it must be finite, say k. Okay. So, that means H of cardinality of a subgroup divides the cardinality of the groups. So, this is the Lagrange's theorem which we prove for the when we talk about left coset, but this can be proved with the help of the right coset also. So, the similar proof whatever we did for the left coset is similar result is followed for the right coset. Now, we want to see the relationship between left coset and right coset. So, that will be more interesting to know. So, we want to see some relationship between left coset and right coset. So, this is we have a theorem on this. So, this theorem is telling the number of distinct left coset is same as total number of distinct right coset. Okay. So, it is telling the theorem is telling the number of. So, we have this, suppose G is here. Okay. So, we have the left coset, these are the left cosets, say BH, CH, DH like this, where A, B, C, D are coming from G, and similar way we can have the right coset also, say HX, HY, HZ, something like that. Okay. Now, this number is same, we know the number of this whatever number of left coset we have, if we have n number of left coset, then there must be n number of right coset. So, that is this theorem is telling. So, if we denote this, so how to prove that? Suppose L is the right coset set. So, L is this sorry left coset set, this set. So, this is the set of distinct left coset. Okay. L denote the set of all left coset. Similarly, if we define R as a set of all right coset, then if we can have a bijective mapping from this to set L to R, then we are done. So, say this is the R is the set of all right coset. So, set of all distinct right coset. Okay. So, now our aim is to have a mapping from bijective mapping from L to R, then we are done. So, let us just define a mapping F from L to R. So, this is we take a left coset H, now it should give us a right coset, we just take the H A inverse. Okay. Now, first of all we need to prove that this is a mapping. So, this is basically mapping means if we take H, this and this is the right coset set. Now, it should be mapped to the same element, but if you take another x h, it should map to the same element, because this is not a mapping. If we have like this, one element cannot go to multiple element, this is not a mapping. So, one element must go to single unique element, unique image, we must get a unique image for a element. So, that we have to justify. So, how to justify that? Okay, to justify that we take so we take x h equal to a h. Okay. So, basically these two are same left coset and we take two element a and h, a and x, and they belongs to same coset, left coset. Now, these two must map to the same right coset. So, that means, if we assume this, we need to show that we need to show basically eventually f of h must be equal to f of x h. So, that means, we need to show x A inverse equal to h x inverse. Okay. So, in order to show this, we need to show A inverse must belongs to this. If we can show this, then we are done. Then the mapping is, I mean, this is a valid mapping, unique image. Okay. So, let us try that. Let us try to prove that. Okay. So, let's. So, if we have this, this means both the way x belongs to h, then only these two are same. Okay. If we take any element from h, then if we make the class that left coset class around that element, that will give us the same element h. Okay. So, now this is basically h. Now, this implies A inverse x must belongs to h. Okay. Now, this implies A inverse x we can write as this way, belongs to h. Now, this implies A inverse belongs to, now this implies x A inverse equal to h x inverse. So, this implies f of h a is equal to f of x a. Good news. So, that means the unique. So, this is a mapping basically. This is a valid mapping. Mapping means one element must go to the single image. This is not a mapping. Okay. So, we take this is a set which is same as x h which is a h. So, they are going to same element. So, that is a mapping. So, this says that this implies F is a valid mapping, F is a mapping. So, now we have to prove that this F is bijective, then we are done. Okay, now how to show F is bijective? Bijective means first we have to show F is 1 to 1 injective. So, 1 to 1 means this one. So, if we take an element, so this is not a 1 to 1 function, but 1 to 1 means this single, I mean, so if you take two element say H B H, and if they are not same, so if you take H and B H, if they are not same, then they must map to the two different image, that is the 1 to 1, and this must be true for any two distinct element H B H. Okay. Now, how to prove that? Suppose we take two element H B H which are not same. Now, what is f of H? Suppose f of H equal to f of B H. Now, f of H is nothing but H A inverse, which is same as H B inverse. Now, this implies A is equal to B H, which contradicts the fact H is not equal to B H. So, this means this is not equal. So, the mapping is 1 to 1. So, F is a 1 to 1 mapping. Otherwise, if we assume their image are same, then they must be same. Okay. So, this is not a, this is a 1 to 1 mapping. Now, we have to show this is a 1 to also, then we can say this is a bijective function. Okay. So, how to show this is 1 to? Okay, onto means, so this is L, this is R, this is the set of all left coset, this is the set of all right coset. So, onto means 1 to 1 means this is, we have seen this is 1 to 1 like this, the mapping is like this. Okay. Now, this is 1 to 1 we have already seen. Now, we need to check the onto part, then only we can say this is onto means if you take an element over here, say H of, this is the right coset H of A. Now, onto means there must be an element over here such that it is mapping to this element, then only we can say this is onto. So, we know there is an element like A inverse H. We know there is an element A inverse H such that f of A inverse H is nothing but H of, so this is basically H of A, and this is true for all A. So, this is the onto. Okay. It is covering the whole set on the this. So, this is basically onto function, onto mapping. So, hence F is bijective. So, F is a bijective mapping. Okay. Since F is a bijective, then so their cardinality is same. If we have a bijective mapping from one set to another set, this is L set, this is R set, it is covering all the elements. So, their cardinality is same basically. So, cardinality of L and cardinality of R is same. So, there are same number of, so if we have a left coset, then there are same number of left coset and there are same number of right coset for G. Okay. And that number is called index of H. that common number is called index of H. So, that is also denoted by this way G hyphen H. Okay. Now, if G is finite, then order of G is basically order of H, because into the index of this. So, basically index of this is basically order of G plus order of H. So, this is the when G and H when G is finite. Okay. Thank you.